Hello everyone, welcome back to Electronics 1. Let's take all this material that we've been introducing over the past few lectures and investigate how it applies to specifically a diode to get the behavior that we've already previously looked at from the terminal perspective. Okay, so let's look at a PN junction diode that is formed from, as the name suggests, a piece of material that's doped to be P-type and a piece of material doped to be N-type. And very often the material is silicon. Okay. So before we actually form the junction, let's just show our two pieces of doped material that are P-type and N-type. Okay, so we know that now when a material is doped to be P-type, we end up with an excess of holes due to adding impurities that are trivalent or that are absent or have 3 valence electrons, which end up resulting in a hole that is not bound, and thus we get what we refer to as our majority carriers that are holes in our P-type material. Okay, so we'll have majority carriers of holes, and this P-type material will still have minority carriers that are generated thermally, which of course will be electrons. Okay. One of the more common impurities to create a P-type material is boron. And this is known as an acceptor impurity, okay, or the doped with an acceptor atom, such as boron. Okay, in our N-type material, we have a surplus of electrons, or majority carriers that are electrons. So in the N-type material, we have majority carriers that are electrons, and we have minority carriers that are holes. And just a reminder, right? The large letter here refers to holes or electrons. The subscript is referring to the material that we're in. So in this case, we're in the P-type material, whereas over here we're in N-type. Okay, and I'll reiterate again that a few things, but it's important to note that both pieces of our semiconductor above are still electrically neutral, right? We added in acceptor atoms, boron, in our P-type material. We added in donor atoms such as phosphorus in our N-type material, but those atoms themselves were neutral, or those impurities were neutral. The silicon itself beforehand was neutral, so we have not changed the charge of the semiconductor. They're still electrically neutral. Okay. Another thing to note is that the majority and minority carriers are distributed uniformly throughout the material. This shouldn't be surprising after our discussion about diffusion, and that the desire of our materials is to reach a uniform distribution, and if there is not a uniform distribution, we get diffusion current, which we're going to revisit here in a second. Okay, so this is the case. These notes apply to this case where we have a individual isolated piece of p-type material, we have an individual isolated piece of n-type material. But now we want to go and join them together to form our diode, our p-n junction. Oops. Okay, so now rather than two individual pieces of semiconductor, doped semiconductor, now we have two pieces that, and I'm going to kind of show this in steps. So here is when we first join the two materials together. These positively charged holes are going to want to move to the right. These negatively charged electrons are going to want to move to the left, and this is to counteract what is now a very clear concentration gradient between the two halves of the material. Okay, so to try to reach a steady state where we have a uniform distribution, these holes are going to want to move to the right, the electrons are going to want to move to the left to try to stabilize that that mismatch in concentration of holes and electrons. Okay, this point where the two materials are put in contact with each other are known as the junction. Okay, and when we defined diffusion current as I subscript d back a few lectures ago. So although you may think about diffusion is happening in both directions because we have electrons to the left, holes to the right, in terms of the conventional direction of current flow being the direction of movement of positive charge, the direction of diffusion current is going to be from left to right. That's the direction that positive charge is moving. Negative charge is moving the other direction, but even the movement of negative charge we would consider the actual current flow to be in the opposite direction of that. Okay, so we have we'll call majority carrier diffusion that is in the direction from left to right. Okay, just to put that into words here, our holes from our p-type are going to diffuse to the n-type, and our electrons are going to diffuse from our n-type to the p-type material. Okay, but as that diffusion current takes place, we're going to have some recombination occur. Right, we have holes moving towards electrons. It's not surprising that we're going to have recombination. So this recombination will take place close to the junction. Okay, and by recombination we mean that holes combine with electrons in the n-type material, and electrons combine with holes in the p-type material. Okay, now, so keeping in mind that the p-type material was initially neutral, right? When we started out with the two separate pieces of doped semiconductor, so that p-type material was initially neutral, but now we've essentially removed some holes as that recombination occurred, or as the holes made their way into the n-type material. Okay, so removal of holes from the p-type is going to result in a net negative charge in that p-type material. Okay, so we end up with a net negative charge in our p-type due to those holes traversing across the junction, and of course the opposite will occur, the removal of electrons from the n-type results in a net positive charge. Okay, and again, this removal of holes is due to this, or electrons is due to this diffusion current that we looked at here, right? As these holes move in this direction, electrons move in the other direction as they cross into the material on the other side of the junction. Well, that leaves, you know, these holes absent in the end material, leaves these we can't backtrack here for a second. Leaves these holes absent in the p-type material, leaves these electrons absent in the n-type material, so leaves behind some negative charge in our p material, leaves behind some positive charge, but we also have the positive charge that's moving across here also contributing to a change in the net charge in the end material. And these electrons that are moving across are contributing to the net charge in the p-type material. Okay, so all of that results in a net charge being established in the p material and a net charge, a net positive charge being established in the n material. And this is often described as the charge being uncovered. Okay, so from materials that were initially neutral, we've now uncovered charge, and this happens in the vicinity, in that area around the junction. Okay, so if we look at the figure of our PN junction diode here again in this, so we have our p-type material, still has majority carriers of holes. We have our n-type material that has these majority carriers that are electrons, but in this region around the junction I'm going to have these electrons that have crossed over to create some net negative charge in the p-type material, and due to these holes that have crossed into the n-type material, I'm going to end up with a net positive charge on the n-type, or on the n side of the junction. Okay. And just to, well, maybe we'll come back to this here again in a second as we continue to define this PN junction here. Okay, so now we have a region on both sides of the junction that is absent of charge carriers. Absent, sometimes we call this devoid of charge carriers. Right, because of recombination that has occurred in that region. This region is known as the depletion region. Okay. The other, so that's that region I've kind of shown in green here. This and again the size of it's kind of exaggerated in this diagram, but that's just to make it stand out here. Okay, so that's region here around the junction where recombination has occurred, and we have ended up with some net charge. Is known as the net charge across that region is known as the depletion region. This uncovering of charge that occurs here results in a voltage being set up across the depletion region. And that voltage opposes this diffusion, this natural diffusion process that we talked about happening as a result of these large concentration gradients of majority charge carriers, the holes and electrons. Okay, so this voltage, or also, as we know, voltage can be referred to as a potential, will counteract the diffusion process. Okay, so just to go back here, let's label this voltage difference on my diagram of my diode here. Let's call this V0. It's going to exist across this depletion region or across this junction. Okay, well, if we have a voltage across some difference, some distance, that distance being the width of the depletion region, we're going to establish an electric field. This field does aid in the movement of minority carriers. That approach the edge of the depletion region. Oops. And as a result of this electric field, those minority carriers will get swept across the junction. This movement of charge carriers is, of course, a form of current, and we will call this IS, which is our drift current. Okay, so let's just go up looking at our diagram here again. I'm just going to erase this comment about the depletion region and show this current IS that's due to minority carriers that, as stated, is a drift current. So minority carrier drift current. Okay, so we have this drift current that exists. If you go back, remember before we said due to this difference in concentration, or this concentration gradient, we had a diffusion current, and maybe I'll add the word current on here just to be clear. So if I come back down to my this diagram, right, we also have a diffusion current. Maybe I'll show this with in orange as well here. So we also have a diffusion current going in the opposite direction, and it's because we have those two counteracting currents, we end up actually having no net current at equilibrium, or when equilibrium is reached, because if you can imagine, when this diode or PN junction sitting just on a bench top, we have no means of having a sustained current flowing from one terminal to the other without some external source connected. So these two currents must reach an equilibrium, okay, and there must be no net current. Okay, so no net current, since an equilibrium condition exists. It must exist. Where the majority carrier diffusion which is ID is balanced by the minority carrier drift. IS. Okay, be careful about I know that it can be challenging to remember which current these terms refer to, because the drift and diffusion both are a D, but the I subscript D corresponds to diffusion current. Okay, so again, without any external bias or connection to this diode, or PN junction, the drift current must equal the diffusion current, so that an equilibrium exists. Okay, just to go up to look at this, maybe I'll put it down here at the bottom here again. So just to make it clear what this PN junction that I've drawn represents, this is, in our schematic diagram, what we would show as a diode. Okay, so This is just looking at the internal structure of a diode, where this end is the anode, the p-type material is our anode, and the n-type material is our cathode. Just want to take you to the slides that are available for this class that you can find on D2L. And we have some good graphical representations of this process. So again, here's figure showing our two separate p-type and n-type material that will be used to form our p-n junction, and a little bit more detail has been shown here to added here to show the minority carriers in each of the materials as well. Those are shown in the dark colored circles, show that the p-type material still has some free electrons due to that thermal generation, and the n-type material still has some holes due to thermally generated holes. Okay, and here when we join the two materials together, due to that concentration gradient that exists at the junction, the holes are going to want to diffuse to the right, as shown on the bottom of the diagram, and the electrons are going to want to diffuse to the left. And as they diffuse, some of those will recombine in the junction area, and due to that recombination, we get an area that has no charge carriers, but we also end up with an area of no charge carriers and also a junction potential. Okay, and here in this diagram, that funky Greek letter is what we're going to refer to as V subscript naught, as the junction potential. Okay, and now that a junction potential exists, basically you can kind of view that depletion region as the plates of a capacitor. Okay, so when the any minority carriers in the n-type material, any of those holes that get close to the edge of the depletion region, they're going to experience the force due to the electric field, and of course holes are going to be pushed in the direction of the electric field, and the electric field's pointing to the left, so holes will get pushed to the left. Any electrons in the p-type material, which are minority carriers, if they get close to that depletion region, they're going to be swept to the right. Okay, the end of the day, without any external connection to this p-n junction, all of these currents have to equal out. Right, so any of the any diffusion current has to equal the corresponding drift current. So the electrons that are moving to the left due to diffusion will be exactly counteracted by electrons that move to the right due to drift, due to that electric potential. Okay, and same for holes. Okay, so all of that to say that this process of joining these two different materials together sets up a depletion region and some potential, and due to the exchange of currents, diffusion and drift current, but those currents, again with no external bias, are equal in magnitude and cancel each other out. Okay, so the next class we will spend just a little bit of time looking at deriving that junction potential, right? And as you can probably kind of foresee coming, that junction potential is going to relate to that forward voltage drop that we see with a diode and that we must overcome to get that diode to conduct.